Okay, the next topic here we'll talk about is polarity. To introduce this topic, let's answer this question. Are all spaceships the same? Well, obviously not, right? I bet many of you could name these spaceships from Star Wars. They all have different purposes and abilities, right? And in my analogy, you'll see that the parts around a molecule act similarly to spaceships, okay? So, polarity. When electrons are shared unequally, a dipole is created. This may be a new word to you. Make sure that you know that. Remember that electrons are shared unequally when there is an electronegativity difference between two atoms. Dipoles act like tiny spaceships pushing and pulling on the central atom. Okay? So if you have a central atom here and you were to tether it to some large spaceship and pull it, and then you were to tether it to a smaller spaceship and pull it, it would have a net result of moving towards the stronger spaceship. Just like stronger spaceships, stronger atoms that have a higher electronegativity difference can pull electrons towards themselves. Okay, we're not actually moving the central atom here in this case, but the analogy remains. Okay, if the central atom moves, okay, if it were to move, the molecule is considered polar. If it stays still, again, it's not actually moving, but the electrons are moving away from it. If it stays still, the molecule is considered nonpolar. Okay, so that would be the difference between a polar molecule and a nonpolar molecule. Another way to look at this would just simply be to say if it's symmetrical, then it's nonpolar, and if it's asymmetrical, then it is polar. All right, and this will make more sense as we look at some examples. So, to do this, we need to talk about bond polarity first. Okay, this is the polarity within bonds. And this arrow here shows a partial negative towards the arrow side. That's showing that it's negative, and a partial positive will show that it's the positive side. Okay, so this arrow points towards the negative, and it looks like this part is kind of like a plus sign. So that's how I remember that it's the positive part. So let's look at a few examples. This bond right here, right there. Hydrogen has a lower electronegativity value than oxygen does. So the dipole, okay, remember this is the dipole arrow. The dipole points towards oxygen. Likewise, on this side as well, the same thing is happening. So in both cases, the dipole points towards oxygen because oxygen is more electronegative. Down here in carbon dioxide, oxygen, again, is stronger than carbon on both sides. So the dipole points towards the more electronegative, and that would be oxygen in this case. And then lastly here, carbon and hydrogen are almost identical in their electronegativity values. I would give the edge slightly to carbon, but the obvious one is fluorine here. Fluorine is the most electronegative atom, so the dipole points towards fluorine, and this bond right here is very polar. Okay, so bond polarity is pretty straightforward. You just compare the electronegativity values of the atoms that are participating in the bond. Now, if we were to look at the entire molecule polarity, it's a little different. If you've taken physics, as I know some of you have, these act as vectors, and you add the vectors together. So let's look at some examples. You need to determine the bond polarity first In CCl4, carbon tetrachloride, you have carbon in the middle and sort of like a tripod shape. You have chlorines all around. The dipoles would point towards the chlorines, right? Because chlorine has a higher electronegativity value. However, if you draw all of these out, you'll quickly see, because this is tetrahedral, all of these cancel, okay? And the carbon atom, if it were tethered to really strong spaceships, it wouldn't move anywhere. So this would be a non-polar molecule. Okay? Let's look at this one. Carbon dioxide, likewise, has those dipoles, just like we showed here. But because they're equal and opposite, carbon stays the same, and this would also be non-polar because it is perfectly symmetrical, if you can see that, the left and the right side. Water is H2O, and it has two dipoles that point like this, right? But the overall dipole that exists here is this one shown in black. These two dipoles, bond dipoles, add up together to form an overall dipole, which points towards oxygen. So this is very polar, and that's why water is a polar molecule. NH3, likewise, has the same thing going on. The bonds have hydrogen and nitrogen. Nitrogen would be the strongest of the two, and the three dipoles that point towards nitrogen add up to this overall dipole pointing towards nitrogen. And in fact, nitrogen is so strong it retains this lone pair here. So this would also be very polar. Okay, and you'll see that the shapes dictate the polarity. Okay, so bent molecules are polar, trigonal pyramid molecules are polar. Okay, trigonal planar molecules can sometimes be polar, but in this case, it is nonpolar because these three dipoles cancel each other out because this is 120 degrees on each side, right? This would be a nonpolar molecule because of symmetry. So, use the analogy of spaceships pulling on the central atom if that makes sense to you, or just look at the symmetry in three-dimensional space. Remember that some of these, like this one, which is tetrahedral, this one, which is bent, and this one, which is trigonal pyramid, those are three-dimensional shapes. This linear molecule here and this trigonal planar molecule, those are two-dimensional. So you have to remember some of these are three-dimensional. Think of symmetry in 3D. Okay, so whenever electrons are shared unequally between atoms, it's called a polar bond. Whenever electrons are shared equally between atoms, it's called a nonpolar bond. Okay, when they're shared equally, that means that there's no electronegativity difference. As we can see here with Cl2, each chlorine, right, is equally as strong as the other, so it's a nonpolar covalent bond. Although they are sharing these electrons, it's nonpolar. Whereas HCl, chlorine here is the stronger of the two, so it has a dipole that points towards chlorine, and that would be a polar covalent bond because they are still sharing these two electrons. And then lastly, think back to when we talked about ionic bonds. Ionic bonds are inherently very polar. Sodium loses an electron entirely to chlorine because chlorine is much more electronegative, and ionic bonds transfer electrons completely. They do not share them. So that would mean that this is an ionic bond. And we don't draw dipoles for these because they're not sharing any electrons. Okay, so that was just a little review. Here, there's plenty of practice for you here. Consider whether the following molecules are polar or nonpolar. What I want you to do is pause the video, write these down, and draw the Lewis structure for each of these. Once you draw the Lewis structure, it'll be more obvious which of these are polar and which are nonpolar. Okay, so I'll give you some time to do that. Pause the video, and we'll pick up on the next page. Okay, so I hope that you gave these an attempt. Here are my answers. Make sure that you have the correct Lewis structure because it is important for the next step. Once you have these Lewis structures, you can see the shape. Okay, you should be able to see the shape of these, such as this one is tetrahedral, likewise with that one, this one. Okay, some of these are bent, like this one. Some of them are linear, like this one and this one and this one. Some of them have a trigonal pyramid shape, like that one and that one. This one's also linear, and this one is linear as well. And this one. Okay, so you should be able to determine the shape by looking at the Lewis structure. Okay, that is something we've practiced. Now, once you know the shape, you can determine the polarity pretty easily by looking at the symmetry. So go ahead and list whether these are polar or nonpolar. Pause the video and we'll start back up on the next page. Okay, so what we've got here is pH3. Let's go back here. Because it has this shape, it is polar. Do you see why? This lone pair here is different from the base of this trigonal pyramid. So that would make it a polar molecule because of asymmetry. CCl4 is nonpolar because it is perfectly symmetrical, it's tetrahedral. HF is polar because it has one dipole bond and it points that way. Okay. H2S is polar because it is a bent molecule, and all bent molecules, as you'll see, are polar. SiF4 is nonpolar for the same reason that CCl4 is nonpolar, because of symmetry. It's a tetrahedral, and everything around the central atom is the same thing. F2 is nonpolar because it's linear and it's perfectly symmetrical, right? NF3 is polar for the same reason that pH3 is polar. So this lone pair up here makes it different. It's a trigonal pyramid, and as you'll see, all trigonal pyramid molecules are polar. CHCl3 is polar. Even though it is tetrahedral, there's one thing that is different from the other three, and that makes it polar, because hydrogen does not pull as strong as chlorine. O2, just like F2, is nonpolar because it's perfectly symmetrical. CO2, likewise, is nonpolar because both sides of carbon have a double bond oxygen, and it is perfectly symmetrical, so it is nonpolar. Carbon monoxide is polar, okay, because the dipole, the one single dipole for this bond, is also the overall dipole for the molecule, and it points towards oxygen. And then lastly, HCN, hydrogen cyanide, is polar because nitrogen is stronger at pulling electrons than hydrogen, so the dipole points towards the nitrogen. Okay? That's all I have for this. We're going to do a little more practice, as you'll see with this cartoon. and I've got a good lab coming up. Make sure that you understand this. It is very important as we move on towards intermolecular forces. Let me know if you have any questions.